In the first year graduate algebra or algebraic topology, you probably have seen the following theorems. The Five Lemma. If there are 10 objects A, B, C, D, E, and A prime, B prime, C prime, D prime, and E prime, with arrows connecting them, satisfying the two rows are exact, and that arrows L, M, P, and Q are all isomorphisms, then it follows that the arrow in the middle, N, is also an isomorphism. And the snake lemma. Suppose you have a diagram of two exact rows with morphisms connecting those two rows. Then, if we take the kernel and co-kernel of arrows, the vertical arrows A, B, and C, we will get an exact sequence starting from the kernel of A, followed by kernel of B, kernel of C, to co-kernel of A, co-kernel of B, and co-kernel of C. And the short exact sequence of chain complexes induces a long exact sequence of cohomologies, which is also called the zigzag lemma. So A, B, C here are all chain complexes, and they form a short exact sequence. Suppose we have three chain complexes A, B, and C, satisfying each row is a short exact sequence, and each square is commutative. Then there's a long exact sequence induced by this short exact sequence of chain complexes. If we review the proof of all of those lemmas or theorems, we will find there's a communal feature in their proofs. This communal feature is an element using the diagram chasing. Actually, in homological algebra, there's a miscellaneous connection of propositions using the diagram chasing argument. So a natural question to ask is that, can we build a theory to deal with all such propositions all at once? Such a theory already exists, which is our topic today, the spectral sequence. Roughly speaking, the spectral sequence is a theory or a tool for us to do diagram chasing. Now suppose we have a proposition involving a huge diagram, and of course we have to do the diagram chasing in our original way. The spectral sequence. We can simply plug this diagram into our spectral sequence, and the spectral sequence will do the diagram chasing for us. The spectral sequence was introduced by French mathematician Jean Leray in 1946 as a prisoner of the Second World War. When he was in the war camp, he studied topology. Originally, Jean Leray was studying he concealed his expertise in partial differential equations, fearing that its connection with applied math led him to be asked to do the war work. Originally, the spectral sequence was introduced to solve problems involving the commutations of the sheaf cohomology. The spectral sequence in this lecture will look quite different from the spectral sequence Hay studied in 1940s. The idea of the spectral sequence is the following. Suppose you have a morphism f from the object A to the object B in the abelian category, or the category of R modules, or the category of K vector spaces, or the category of abelian groups, whichever you want. And we want to study the property of this morphism. Is it a monomorphism? Is it an epimorphism? Is it an isomorphism? Instead of attacking directly, we may want to think of it in the following way. Let's first extend this into a diagram by adding two zero objects and zero arrows. We know that f is a monomorphism if and only if the kernel of f is 0. And if you think of this in another way, this is equivalent to saying that the homology or cohomology at A is trivial, because when the kernel is trivial and the image, of course, is always trivial, the cohomology at A as a quotient of kernel over image is always trivial. And f is an epimorphism is equivalent to saying the co-kernel of f is trivial. But the theory of abelian categories, or category of R modules. And what does co-kernel of f equal to 0 mean to us? If you look at the homology or cohomology at B, noticing that the co-kernel of f equal to 0 is equivalent to saying that the image of f, which is defined to be the kernel of co-kernel of f in the abelian categories, is equal to B. And this is further equivalent to saying that the homology or cohomology at B is trivial. And what can we learn from here? From here we learn study of the properties of an arrow in an abelian category can be converted into the study of its associated homology or cohomologies. In general, if you have a diagram consisting of, say, objects A, B, C, D, E, F, G, H, satisfying that each square is commutative and that every arrow composed with an arrow next to it is 0, then we will extend this local diagram to a global one by adding zeros. And this global diagram will be called a double complex. In the theory of spectral sequence, we will mainly study two types of homology or homology of this double complex. The first type is the cohomology or homology along each row or each column. The second type of cohomology or homology we study is the homology or cohomology formed by the total complex of this chain complex, i.e., by taking the direct sum of the objects along each anti-diagonal line, and we will form a single complex from this double complex. There will be a differential from a direct sum of objects to the direct sum of objects in the next degree, and each D will be induced by the vertical and horizontal maps. So this is the second type of cohomology or homology we will study. in the theory of spectral sequence. And furthermore, we will study the profound relation between these two kinds of cohomologies. And the connection between them will help us do a lot of amazing things, which can be seen in the examples I will give in this lecture. This lecture will consist of two parts. First, I will give an informal definition of the spectral sequence and give some properties of it. And we will use the informal definition and the basic property of spectral sequence to compute a couple of examples. So this is the first part of the lecture. In the second part, we will give a formal definition of spectral sequence. We will see how exactly the spectral sequence is constructed and verify the properties we mentioned in the first part. And in particular, we will prove this fact: the connection between the cohomology along each row or column and the cohomology along the total complex. The connection will be a special case of a theorem called the filtration theorem, which reveals the connection between the objects in the spectral sequence and the cohomology along the total complex. So this is the structure of this lecture. And in this lecture, we will follow Professor Ravi Vakil's book. And this is his section 1.7. We'll use same labels and notations as he does.